C. Undisturbed layers, sedimentary rock, the lowest layers contain the older rocks. Make sure there's keywords you're looking for. You're looking for undisturbed, and you're looking for lower is older. You have to make sure both those are correct. Moving on. All right, two-part question looking at the diagram. It's asking which fossil would be most helpful in determining the relative age of the rocks. Which one of those fossils? Here. Which letter?
Starts with the B.
It's A. Yeah, ammonite. Which they really don't look blue like that. They just colored them blue for, you know, your purposes. Jason, the screen's up here. Why is that a good fossil to use for relative age? Why?
Because they're in the same layers.
They're all in the same layer, and they're all, you find them in each one of the columns. So they're abundant. They're only in one timeline. So what type of fossil is that? Index fossil. Okie dokie. Now part B. All right, we're looking at two pieces of evidence that describe why these fossils are useful in determining relative age. Now, one thing you can do is a true or false for each one of those. So, for the fossils we just chose, the ammonites, do they all appear in the single layer?
Yes.
That's true. Are they appearing in all but one layer?
Yes.
Nope, they only appear in one layer. That's the exact opposite of what we just selected, so we're going to skip that. So true or false, the fossils appear in different types of rock. Is that true or false? Are they in different types of rock?
No.
Nope, they're all in the same kind. The fossils appear in each column, true or false?
Yes.
True. So if it's true, let's select it. The fossils do not appear with any other fossils in the layer. True or false? False. There's other fossils in there. So it's just those two. They're just in a single layer, and they appear in each column. That's why they make great index fossils. All right. Identical rocks, identical fossils, and similar mountain ranges, they're found on different continents that are separated by oceans. Why are they found on different continents? So the continents were joined together at one time in the past. Who agrees? Does anybody remember back in 6th grade that giant supercontinent that all the continents used to be when they were squished together? Pangea. We know that that happened because we are finding fossils on two different continents that used to be joined together. Like, why would we find fossils in Antarctica and in Australia? Because one time they used to be together. Mountain ranges, they fit together like puzzle pieces. The mountain ranges start on one continent and begin on another continent. They're all part of the same mountain range, and we know that by analyzing the rock layers.
There's one big huge.
What information do fossils provide about plants and animals? Let's do true or false. Animal and plants have not developed together. True or false? Don't make me start calling on people.
True.
It's false. They developed together. Plants and animals have been together for a long time.
Oh yeah.
Animal and plants have not changed over time. True or false? Definitely false. We have evidence that they have changed. Look at the mastodon and the mammoth and the elephant. They've changed. C. Animals and plants have changed only recently. True or false? False, definitely. They've been changing a long time. True or false? Animal and plants have changed over time. Yeah, that's true. All right, images. Test people love to put pictures and test whether the pictures are actually helpful or if they're kind of just there. You need to pay attention to them to see if there's any clues. So in this, which fossil is the youngest? Which fossil is the youngest?
Fern.
It's the fern. How do we know that?
Because it's at the very top.
You guys see that? Top is the youngest, so those fossils are the youngest. All right, same image. Which two fossils would make good index fossils? First of all, we know a trilobite makes a good index fossil because it's in our nose.
Grass
So not gastropod, because we see it in a bunch of different layers.
Anima. Whatever. It starts with the A.
What letter?
F.
Letter F, right here, ammonite. That one right there, it's only in one layer,
Fern.
and it's in each one of the columns.
Would Fern be?
Fern is only one up here. Coral, we see in a bunch of different layers. The crinoid, we see in a couple different layers. So the only one that's all in one single layer, but we see in all columns.
I thought fern would be index fossil.
The fern is only right here.
Yeah, I thought it was
It's only in one it's only in one column. They don't have it in any other columns. The only reason we know trilobite is an index fossil because it's in our notes. The ammonite is the only one that's in one layer, but in all columns. All right, which fossil is the oldest?
Trilobite.
Trilobite. It's at the bottom. It's the oldest, and there's no intrusions to mess us up. All right, diagram saying where fossils have been found. The fossils located in which labeled area is most likely the oldest?
3.
I heard 3 and I heard 4. This is the deal with folding. When you have the folding rocks like we talked about yesterday, you gotta pay attention to where the layers are moving. So this layer's not labeled, otherwise we'd say that was the oldest. This layer is labeled, but it curves. Still the oldest, there's just been some folding happening, so the answer is 3. All right, here is a fault line. The fossil at point X, right here, is 65 million years old. So if we use relative dating or law of superposition, what do we know about fossil at point Y?
C.
Nope. We don't. Distortion of the organism by the fault? Nope. D. They both live in the same time period. If you pushed that fault back where it was supposed to be, those would be perfectly lined up. All right, using the diagrams, determine the order of events for the stratigraphic column. There's that word, strata. So this one is the one I told you. Order of events means you start at the beginning. So the oldest. Which one is the oldest? It is C. Even though it's tilted, it's still the bottom layer. What's next?
A.
H is what's next?
E.
E's next.
So why don't you start from the top?
Because we're starting at the oldest.
Won't you put the oldest ones at the bottom? Right.
No, it says determine the order of events. So you start at the beginning, which means you start at the oldest. That's why I mentioned that at the beginning before y'all did your warm-up.
Oh, I did it backwards.
Yeah, a lot of people did. That's why I mentioned it. It's like when you tell a story, you always start at the beginning. So if it asks you what the order of events, you say what happened first. First, layer C was formed. Then layer H, and then layer E. That's the order in which it happened. All right, what comes after E?
And then D. No, A.
D.
It's A.
Wait, would D be intrusion?
Mm-hmm. Remember, intrusions are younger than the layers they go through.
G.
So G would be next. All right, it's there. Cool. All right, what's next?
A.
Next is A. Because A didn't go into F, it stopped at G. Whoops. Go. Nope, that's right. C-H-E. A. Then what?
C. H. E. A.
We
G.
went here, 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 here. Now what?
And then G.
G's next.
We already did G.
Yeah, we already did, she moved it.
Oh, yeah, I did move it, didn't I? Move back. Move back. All right. Here, 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 here.
And then
All right, we're here.
D.
A. And then what?
F,
Is D.
it's F.
Fight, fight, fight.
D with
So, intrusions are younger than any layer they go through.
F.
So which is older, D or F? F is older. And what's next?
D.
D. And then the top layer, the youngest, is B. So that's it. Remember, A is younger than all the layers, G, E, H, C, but is not older than F because it didn't go into F. It left F alone. D is younger than all of them because it got up almost all the way through F. The only thing that's younger than D is B. Layers of rock are known as what? Strata. Alright, here's a diagram. This one, there's part of it that should have been a little confusing, but the rest of it should have been fairly straightforward. We've got two things going on here. We've got intrusions and we've got a fault line. Fault lines work like intrusions. They are younger than the last layer they push through. So if we're doing the order of events, we start at the oldest first. Which one's the oldest?
E.
E. So E, even though it's kind of crooked because of the fault, it's still the bottom layer. Whoop. All right, what's next?
And then G.
Yep, G. G is the next layer on both sides. What's next?
C.
E.
Ooh.
C.
So we got E.
No, it's
We've got G.
it's D. It's
It's
D.
E.
We already did E.
It's D.
It is B. Because if you push those up, you would have E, G, B, E, G, B. Oh, it's still there. Cool. All right, what's next?
D.
D. It is working like an intrusion. So all these layers were here when that earthquake or that shift happened. The layers that aren't messed up by the fault, those are newer than that fault. They weren't there when that fault occurred. So D is the next oldest. Wait, did I do B? No.
You gotta change.
Go back. All right, so we've got E, we've got G, oh no, we got E, G, B, D. What's next? A. It's an itty bitty layer that's squiggly. That just means that it's usually a weathered rock layer, a very tiny weathered rock layer. Okay. Boop. All right, what's next?
F.
We already did G. Next one is F. Why is C the youngest?
Because it went through all of them.
It went all the way up. It went through all the layers, so it is brand new rock in relative terms, so it goes last. It's the youngest. Yay for us. Oh, I didn't answer one. My bad. Leave. All right, so those are the type of questions you will find on benchmarks, EOGs, so be ready for those. They're going to give you a picture. They're going to be like, what's the youngest? What's the older? Which is younger or older, A or B? If a fossil is found in layer F, is it younger than the fossil found in layer W? Just be ready for that. All right. I want to do hands-on activity using Twizzlers today, but we got to get through our notes first, and there's not a lot of them today. Yesterday we talked about what type of dating? Relative, which means law of superposition. We basically talked about which is older, which is younger, what we just practiced with our warm-up. Today we're going to talk about absolute dating. So we're going to talk about how do scientists determine actual numbers, actual ages. And that's through radioactivity. You do not have to draw the radioactive symbol. I just did because I thought it was cool. Okay, can you see from over there? All right, when we're talking about absolute age of something, remember we're talking about a number, whether it is your absolute age of 13 years old or the rock's absolute age of 1.9 billion years old. It's a number. It's specific. You may also see absolute dating as radioactive dating, because we're looking at radioactive isotopes. Or you can see it as radiometric dating. I want you to be sure you know all those terms, just so if it's on a test question and they say, what's the radiometric dating? that scientists use for fossils, you'll know they're talking about absolute dating. Now, we talked about this process a little bit whenever we first introduced the vocabulary. Was that a week ago? Last week? Yeah. There are a lot of details you can go into with this process. You can get down to the atomic level, talk about the protons and the neutrons, and how they decay. But we're just going to talk about the concept. We don't need to know all that just yet. Who remembers, in 7th grade, I know it's been forever, but who remembers the meiosis and mitosis? You had the parent cell and the daughter cell. Does that ring some bells? Scientists love to use those terms, and they use it in geology as well, with radioactive dating. So, and everything on the planet has some sort of radioactive isotope. Everything does. Over time, those radioactive isotopes start to decay. Then they're no longer radioactive. Then they're stable isotopes. The radioactive isotopes scientists call the parent isotopes. Think about how, are y'all's parents unstable sometimes? Yeah. So, think about that. Y'all's parents are unstable. They're radioactive. That's the parent isotope.
I mean, like, they can't walk or something?
No, like you ever see somebody like, she's out of her mind. She's unstable. So think about stable is termed the daughter isotope. All y'all ladies got it together. You're stable. Gentlemen, don't say a word. So the parent isotope is the radioactive one. The stable daughter isotope is not radioactive. So scientists, when they measure fossils and rocks, and they measure the amount of radioactive material, if the rock or fossil has a lot of parent isotopes, it's not very old. But after a rock or fossil's been sitting around for a while, and it loses those parent isotopes and they become daughter isotopes, then scientists like, yo, that rock's old. It doesn't have hardly any radioactivity left in it. Can you put down some calculator, please? All right. Half-life was one of our vocabulary words as well. Half-life is the point in time in which half of the sample's radioactivity is gone. It's changed from parent isotope to daughter isotope. And that number depends on which radioactive isotope there is. There's more than one out there. For example, the half-life of the isotope carbon-14 is 5,730 years. So every 5,730 years, a fossil loses half of its radioactivity in carbon-14. The half-life of potassium-argon isotopes is, what did it say? 1.26 billion years. So it takes a lot longer for that isotope to lose half of its radioactivity. And the way I drew it out was on pie charts. If you're looking at two different samples, if you have a sample that has a lot more parent isotopes than daughter isotopes, it's a younger sample. That means that the rock is not that old, or the fossil is not that old. I mean, it'd still be old compared to us, but not compared to like Earth history. If you have a sample that has a lot more daughter isotope than parent isotope, you've got a much older specimen. So if you get a test question that says you measured the radioactivity of a fossil and it was shown to have very few parent isotopes left, what can you conclude about that sample? And you can say, oh, well, it's really old. Like really, really old. Yeah, that's better. Now, depending on what we're looking at, what our sample is, that depends on how we're going to measure it. We talked a lot about carbon-14. As far as dating, it's not the only isotope out there, but it is the isotope of choice when finding the absolute age of organic matter. What does organic mean? Not like, no, not that type of organic. You're thinking like organic fruit. I'm talking about if something on the planet is organic. What does that mean? It was once alive? Yeah. If you have an organic sample, it is a sample of something or part of something that used to be alive. All living things contain carbon. No matter what it is, if it was alive, it contained carbon. So we check out carbon's radioactive isotopes, carbon-14. The bummer part about carbon-14, its half-life is only 5,730 years. So that means that those samples lose their radioactivity very quickly. So if you're wanting to find the absolute age of something organic that's really old, that's not going to work. You will not be able to measure it.
Is that matter in this? Organic matter?
Yep, organic matter. Two other ways that are very popular with geologists is the potassium argon isotope and the uranium lead isotopes. Potassium argon is great for dating igneous rocks, especially if the rock is anywhere from 100 million years old to billions of years old. Uranium lead, the potassium argon is the one that's 1.26 billion years half-life. So it takes a potassium argon isotope takes 1.26 billion years to lose half of its radioactivity. Uranium lead has a half-life of 4.46 billion years.
Is that a T in between uranium?
No, uranium dash lead.
Oh.
Portion dash, whichever you prefer. Slide your dash. So it takes a sample that contains uranium lead isotopes 4.46 billion years to lose half of its radioactivity. So you want to use uranium lead isotope measuring for rock samples that are billions and billions of years old. Those rocks at the Grand Canyon that are 1.9 billion years old, you would use something like potassium argon or uranium lead to measure their radioactivity, to figure out how old they are. So the star down there says we cannot use absolute dating on fossils unless it's carbon-14 or sedimentary rock. Why? What's sedimentary rock made of? Sediments. And what are sediments? Broken pieces of what? Rock. So you cannot find the age of a rock that's made up of thousands of other rocks. You have no idea which rock was oldest, which is youngest. It's too much. So there's no way to determine the exact age in which sedimentary rock was formed. It's not possible. However, if you're digging and you got this big old layer of sedimentary rock, but in that layer you find chunks of igneous rock. All you gotta do is find out how old that igneous rock is, and you know how old that whole layer is. So you're using absolute dating on igneous rocks to find the absolute date of the sedimentary layer. Same with fossils. Unless you have any organic matter left, you cannot use absolute dating on fossils because they basically turn into rocks. So you gotta use the igneous rocks around it, or hope you still have some organic material left, like as in that mummy. Alright, once you have completed your notes, you can shut your notebook.
Hold on, I'm not done.
Mm-hmm.
Wait, what did I say to your igneous rock?
Contained.
Igneous rocks contained in the sedimentary rock layer. So right now I have Kaden, Tiana, Maya, and Alex who are getting a grade for their worksheet. Everybody else is taking a 0.
What?
I'm gonna find it between by the end of the day. Don't start off the quarter like that.
What word you keep?
Somebody fill him in.
Is there any more papers?
Is there any what with the what?
More other papers?
You mean Kendrick Washington?
I don't know what it's on.
That's my cool dude. everybody should have a piece of graph paper. Make sure your name is on it just in case stuff gets mixed up. We are going to pretend that we have fossils that have organic matter in them, and we're going to know how old they are. So if I have a fossil that contains organic matter, which isotope am I going to want to use to find the age?
Parent.
Which one? Do I want to use uranium, potassium, or carbon?
Carbon.
I want to use carbon. If I have organic matter and I want to know how old it is, I need to use carbon 14. Everybody got these notes? Anybody still plugging and chugging? Nope. Okie dokie. All right. On your graph, I want you on the left axis, right, Twizzler height. On the bottom axis, I want you to write half-life years. Every group should have a calculator at their table somewhere. When I pass out the Twizzlers, do not eat them. Because you're going to need them for an activity. Even if you eat them, you're not going to be able to do it.
She dropped my food. You not eating anyway. Oh. Alright, so these are our fossils.
She's got the fresh one.
Yeah, they're all freshly. Sorry, sit down, please. So the Twizzlers are our fossils with organic matter. We're going to be finding out how old our Twizzlers are by using half-life. Oh, I need to.
Oh, what the?
So we're going to measure the Twizzler height on our graph, starting in the first column. So you're going to lay your Twizzler in the first column, and then however tall your Twizzler is, you're going to mark it in the column.
Oh my, Twizzler's higher than the column.
So you're going to put a dot, put your Twizzler lining up with the bottom of your graph, and however tall it reaches, make a dot. Even if it goes above the graph, it's okay. the bottom of that first column, I want you to mark it as first formed. This is when our organism died and started turning into a fossil. I mark it as first formed. Instead of doing your warm-up, you need to get the notes that you missed yesterday. Because you can't do a warm-up without them.
The notes from
Starting here. And then we include this thing in that we did the other day.
wasn't
And
here.
then,
you said my Tuesday I wasn't here.
yeah, yesterday. This is what we did yesterday.
Yeah, I wasn't here.
I know, that's what I'm saying. You need
So
to
copy
get
the
these notes and not do the warm-up for today.